And now what we're going to do is we're going to work methodically, step by step, on a set of 6 data files that we're going to construct as we go. And we're going to run them, and I'm going to talk about all kinds of things as we go. Okay. So that's the next step here. So this is all going to live in the world of where it says tutorials. And there's separate directories for these separate little projects, okay? And they're numbered 1, 2, 3, 4, 5, 6. So we're going to go through them sequentially, okay? So first of all, I'm just going to open up a text editor, and here we go, 1collide.p2dat. That's my designation for a PFC 2D data file. So if I just look at this, it's just a text file. Model new, blah, 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 program return. That's the return where it's going to just go here. Now then here's a bunch of notes to myself about what I'm going to talk about. But there's comments. The semicolon is a comment character. Okay. So we're going to go through these step by step and talk about all sorts of stuff as we run them. And then it would be useful for you to go through them yourselves. And you've got all the stuff we're going to discuss down here. So just to make sure that all this stuff makes sense. So I'm going to fire up PFC from scratch. Let's not have a project at all. I'm just going to fire it up from scratch. So I'm going to go to my desktop, and I'm going to do PFC 2D version 7, subversion 157. And then I'm going to say new project. And now I have to navigate to where those tutorials are. So I'm working on it. Tutorials, 1collide. So I'm just going to call this Collide. The project name will be Collide. Boom. There we go. Project name, collide.prj. So then I'm going to say File Open. And there's a data file. So I double click it. Boom. And that's the data file, right? What's this data file going to do? It's going to make two particles. Think of them as like 2 balls on a billiard table. One of them is going to be stationary, and the other one's going to be given an initial velocity, and it's going to smash into the ball and make it move. So let's just run this. So I haven't done any cycles yet. So I want to look at the system. I want to look at the balls and the axes and all that. So by default, there's always a plot window here. So it's plot 01. I'm going to give it the right finger, and I'm going to rename it. And so I'm going to call this my view. And now I have to add plot items. So I'm going to go here, and I'm going to say ball plot item. There it is. I'm going to color them yellow. I'm going to make the thickness of the outline less than 10. Make it 4. Make it 3. All right. I want to show the axes. So somewhere on here, miscellaneous, right there is the axes. And I'm not fixed. There's the axes. I can make it a little bigger. So let's see if that made sense. So again, model new, clear out all the memory. You got to say large strain true. There's my title. I got to give a domain. So it goes from -10 to 10. And if you don't give the other one, it goes -10 to 10 in all directions. Linear contact model with these values of Kn, Ks, and friction coefficient. I'll tell you what this is in a minute. Model orientation tracking. And here's the ball create command, right? So I want to create one ball at 0, 0, and I want to create another one at 2.6. And the one at 2 and 0.6 has a bigger radius. That seems right. There's the bigger one. There's the smaller one. When I created the balls, if I want, I can specify a unique integer ID associated with them. So ball 1 was at the origin. And so that's the ball that I'm going to give an initial value of X velocity to. That's why I'm saying range ID 1. So this only applies to ball 1. If I run it to there and I look, attribute velocity X was initialized in 1 ball. Okay. So now if we run this, so essentially we've got this. This is the guy. Let's turn off the axes. This is the guy. This guy's just sitting here. By default, all the velocities are 0. This guy has an initial velocity in the x, like this. So what we expect is it's going to come, it's going to hit this guy, a force will develop, it'll push this guy up into the right and up, and this guy will probably bounce back because he has less mass, because he's smaller. And I must have given a density somewhere. There you go, right there, ball attribute density. I didn't give a damping factor, so there's no damping in this model. Okay, so that's why I call this collide. So if I run this thing, let's do cycle 200. Also, I'm going to say, well, let's just run it and watch what happens. Cycle 200. Boom. It hit. Let's run it again. Cycle 200. Just watch. Watch now. Cycle 200. Go. Boom. So this guy moved up and to the right. This guy moved back. Couldn't really see what was going on. So I want to make the plot interval when it refreshes every single cycle. Well, I'm going to go up here. Tools, options. Even I don't remember this. Plots. There we go. Options for the plots. Right here, update interval. It's currently at 10. I'm going to make it 1 and say apply. Okay. Now let's run it again. You might be able to see it a little bit better. Boom, pushes away. You can see why I do this with PFC version 4 when I did all those simple examples, because I can't make this run slow enough to actually see this. So there we go. Let's see. And we've already talked about this. If I do the question mark, click, that's ball 1, click, that's ball 2, just like we thought, right? Now let's look about what's happening. Did these guys start to spin? What would you expect? Are they going to spin? What direction is this guy going to spin? He's getting hit from below here. Let's see. Let's cycle 200. And now let's say ball list attribute spin. So ball number 2, because this big guy was ball number 2, has a positive spin, and we use the right hand rule. So therefore, positive spin is counterclockwise. The bottom one, what way is the bottom one going to spin? Let's look at this, work this out. I'm trying to, again, if I was at the board, this would be better to do at the board, but I don't have a board here. So it's hitting like here, right? So think of it this way. Again, there's a equal and opposite force. So this guy there's going to be a contact there. Let's say that's the contact location. Let's make this red so we can see it better. This is going this way, right? Well, I can decompose that into a normal component, which is going towards the centroid, right?
Yep.
And I can rotate this, rotate right, and a shear component. Let's make these guys blue so we can see them better, right? Pretty good, right? So that's what I decompose that thing into, right? And I can move that. So this guy is acting here. The shear component is acting here. And so clearly, right, this shear component is this way. So the ball wants to spin counterclockwise, right? And I can do the same thing. There's going to be an equal on this guy, because remember, they're the same thing. There's an equal and opposite thing going on. So here, this guy is getting pushed this way, and this is equal and opposite. So this guy is getting pushed this way. So they're both actually spinning in a counterclockwise way, because that's the direction of the local shear force acting on the guy. Okay, and that's what this is telling us. It's telling they're both positive. So right-hand rule, they're both spinning that way. Now, what's this orientation tracking thing? So here's what that is. I'm going to run it from the start again. And now for the ball plot item, I'm going to click orientation and click it. And so what that's going to do is it's going to put a stripe conceptually of paint onto each particle. And that stripe is going to rotate with the particle. So now if I do cycle 200, you can see that both of them are going counterclockwise. You with me? Okay, so these stripes are going to be useful, and there's the same thing in 3D. In 3D, it draws a stripe all the way around the particle. And this stripe orientation, notice I can say normal direction. If I say 1, 1, I can orient the initial stripe any way I want. Okay. So in order to that takes additional computation energy, right? We have to keep track of where those stripes are. So that means you have to actually turn that on. So you say model orientation tracking on, and then that's going to allow us to be monitoring that. And then there's a whole command, specify the orientation tracking state, right? Okay. All right, now here's the next question. Next question. Okay. So what I want to do now for ball 1, so okay, this collision here, and let me put this orientation back to be up and down, okay? This collision is completely following Newton's law, F equals ma, because we have this concept of degrees of freedom. And in the 2D model, this guy has 3 degrees of freedom: translation X, translation Y, and rotation about the Z, okay? We have a concept now of each degree of freedom can either be free or it can be fixed, okay? If it's free, that means that in that degree of freedom, it's going to obey F equals ma. So that's what a true proper collision would be. And by default, all degrees of freedom are free. But what if we go, for example, and so what's fixed and what's free? It's the velocity of that degree of freedom. Okay, so because we can't, there is no reference configuration, so I can't like fix it so it doesn't move. If I want to fix it so it doesn't move, I have to set the velocity to 0 and then fix it so it remains the same. So let's go and do a little interesting thing here. Ball fixed velocity X, ball fixed velocity X component. And I only want to do that and the spin of range ID1. So what am I doing? For that ball on the left, I'm saying I want your X component of velocity to remain fixed. Wait, is that what I want? Yes. I want your X velocity to remain fixed to whatever it currently is. So the current X velocity initially is 0.5 meters per second. I want that to always stay at 0.5 meters per second. And I want your spin velocity to also stay fixed at whatever it currently is. And by default, it's 0. Okay. So what that means is this ball is going to just keep moving to the right, and it's not going to spin. But in the Y velocity, hold on, let's do this. Let's fully fix everything. We're going to fix all degrees of freedom to stay what they are. Let's see what happens. Now let's do cycle 200. Let's run it again. Now you can see the whole thing. Cycle 200. This guy, ball, list, attribute, velocity. Notice ball 1, I had fixed everything. So his x velocity is still 0.5 and his y velocity is still 0. And he did not spin. You can see he did not spin because I fixed that. Okay. Whereas this guy, all his degrees of freedom are free. So I'm fixing this right now. What if I did one thing to test you to see if you understand this? I'm going to leave the y velocity free for this ball. And what do you think is going to happen? So if the y velocity is free, this guy is going to be free to respond to the force F equals ma, which is going to make him start going down. All right, so now if I do cycle 200, he starts going down. So this would be similar to, think if I had this guy and I shoved a stick through it, and I took the stick and I moved the stick at a constant velocity in the x, and it's a stick, so it can't rotate, but then it was free to slide up and down the stick. And so that would be what this boundary condition is. That's why this guy keeps moving and doesn't spin, but he gets smashed down. So this is what we have in the world of PFC, really. That's all you have. You have these particles and you have these walls. The walls are simply surfaces that you give velocities to, end of story, and they just move at those velocities, okay? The particles have mass, and so by default, all their degrees of freedom are free, and they obey F equals ma. But you might have certain boundary conditions, and what you can then do is make the velocity be fixed, both rotational and or translational. And that means that particular degree of freedom always stays fixed and can't change. Okay. So like if you want to like have a big box of particles and then you glue them together and then you want the bottom layer to be completely fixed, meaning it can't move or spin at all, what you would do is you would identify the bottom layer by saying range, y position, blah, blah, blah. And you would say ball fix, and then you would set the velocities and spins to 0, and then you would fix them all. And that would be how you give that sort of a boundary condition. Okay. And the only other thing you do in terms of the world of PFC is you can have an externally applied force that will act on a particle. But that's it. So you're either fixing the velocities or leaving the velocities be free to do F equals ma, and you may be applying external force and or external moment. That's it. There's nothing else that you ever do in a PFC model. Okay. All right. Let's look at that contact force developing. Just going to run the one here where everything is free. Okay. And what I want to do is, oh, wait, the next one. Let's run this again. And this is back to the other one. So cycle 200, it bounces. They both start to spin as we talked about because that shear force builds up, right? That shear force is building up, makes it spin, right? Now, what's going to happen if we just make one change here? We're going to comment out in the CMAT, whenever we create a contact, we're not going to assign a value of friction. So by default, friction is 0. Okay. So now I have the friction coefficient is 0. What's going to happen when I run this problem in terms of the motion of these guys? The shear force, just a second. has to always be less than the friction coefficient times Fn, right? So if the friction coefficient is 0, the shear force has to be 0. And if there's no shear force, it's only the shear force that can make something spin. Okay, if you think about it, because that gives you an unbalanced moment. And it's the unbalanced moment that makes something that contributes to rotational motion. So we're going to run it now. And we should see a frictionless collision. And you can see they're not spinning. Okay, so there we go. Now, let's go back to the way it was. Let's run this again. Now this time though, I'm going to say, I'm just going to cycle. Oh, wait, one other thing. In order to see in this plot the total number of cycles, I want to see it up here. So what I always do is go to legend, and one of the things I can check here is step. If I check step, it's going to display in the legend the total number of cycles. That's going to be useful. And usually I set that up to do that. So cycle, I'm going to just cycle, what am I going to cycle? 63. Boom! Let's look at what happened. Did they touch yet? Can you see they're not touching? See that? Just one step before. I guess I got lucky, 63. Now I want to add the force chains. I want to see force chains. So I'm going to say, wait, let's turn off orientation. I want to say plus the contact plot item. Draw them as a shape of cylinder. Text value, force chain, scale by force directed. Those two guys there. Now, I'm going to cycle 1. It's just not quite touching. Cycle 1. Cycle 1. There, boom. There's my force chain. Let's look at the color of it. Let's make compression be black. Tell PFC. Sometimes you make changes to this and you got to force the plot window to update itself. So you have to go over here, and this is regenerate the current plot. It's there. Now it's black. So notice this is the force chain. This is exactly the picture that I had there. It's that red guy, right? That's the orientation of the force chain. But now, as I start to move away, this force chain is going to rotate. See if I can see that. There, now it's going to rotate, because now it's ending up pushing away. And there we go. And now they're going to, now they're just moving apart. Right? They're moving apart. Okay. So this force chain stuff is quite interesting, and it's there's quite a big change that was going on as that local coordinate system kept reorienting itself in response to that collision. That's what I wanted to do there. Now, one last thing. Let's go back to this. See, you wouldn't believe we could spend this much time on this like totally trivial model, did you? Now let's just run it a huge number of cycles. I don't know, cycle 25,000. Boom. Now, oh my God, I'm lost. So I'm going to go down here, click on reset to model extent. It's still running. Let's make it stop running. I have to hit, if I hit escape, it tells me use shift escape to stop processing. Okay, shift escape. There, it interrupted the cycling. It's taken 7,434 steps. But where's the balls? So I'm going to go reset to model extent. And I can't even see them because they're so small. Let's look at the domain and do reset to model extent. There's my domain. It was from -10 to +10. And my balls, let's run it again and look at this. Let's run it here. There they are. And boom, they got destroyed. Okay, notice with this periodic domain, you can set the conditions on the boundary. So we can say if a ball happens to get to the domain, just destroy it. It's not in our world anymore. We could also say, for example, stop. So CMAT domain, model domain, and I don't remember how to do that. So model domain condition stop. Model domain extent condition is destroy, but now condition is stop. So now if I run it, and when it hits the domain boundary, it just stops. Okay. Again, you don't want to be hitting the domain boundary. That means probably something weird has happened to your model. But that's what's going to happen. You can also, I'm going to mention, make the domain boundary be periodic. So what does that mean? Periodic means that anything that goes out of this side, if it starts to poke its nose out of this side, it starts poking it in on this side. It's as though this was a sheet of paper and we wrapped this side and made it into a tube and connected it to this side. So we have this periodic space in that X direction. And then it'll also be periodic in the Y. And so if you have a periodic space and you make a packing, for example, in a periodic space, it's as though you have like an infinite system. Okay. And so that's sometimes useful. Like, for example, if people are doing a shear box test, so then you might have something like this, and there's a packing of particles, or let's say you have it like this, and you have granular material in between, and you start shearing this, and you want to see what happens. Well, if you made this boundary X and Y be periodic, then basically anything that goes out here comes in there, and that's sort of like a representation of, in a sense, a periodic space, an infinite type thing. Okay, so PFC has general periodic logic, and it gets done by using the domain. Okay, that's what I wanted to mention there. All right.